This is the Chapter 2 Derivatives Test Review, number 2, the second test review worksheet here. All right, number 1, given x squared y plus y squared is equal to 2x, find dy dx. Notice that this is not going to be a function. The x and y's are mixed together, so we have to use implicit differentiation. And again, the rule with implicit is that when we find the derivative for each term, if we come across trying to find the derivative for variable y, then we have to attach a dy dx once we find that variable's derivative. Now let's look at this equation here, x squared y. So x squared and y, we have to go through product rule here as well, because these two variables are related to one another by multiplication. So product rule is f prime g plus fg prime. So let's go through the rule here. X squared becomes 2x, because that's the f prime, okay, times g, so the g is the original function, which is y. So we're halfway through, plus the f function, which is x squared, times the derivative for the g function, which is y. So the derivative for y is going to be 1, but because we're involving y's derivative, we have to attach dy dx. So x squared times 1 times dy dx. So that takes care of the derivative for x squared y. Plus, so now we're ready for the derivative for y squared. So the derivative for y squared is 2y, but again, we're involving y's derivative, so we have to attach dy dx. Okay, equals, the derivative for 2x is simply 2. There's no need to attach a dx over dx. Because x is the independent variable, it'll just wash out. We only care about trying to keep track of these dependent variables for y. All right, so once we have the derivative found for each term, now we're going to isolate and solve for dy dx. So the terms with dy dx will group together on the left side. I'll move the 2xy over to the other side, make it change signs, 2 minus 2xy. And then now I can factor out the dy dx, which leaves me with x squared plus 2y in parentheses. Divide that over to the other side. So we get 2 minus 2xy over x squared plus 2y. So this is essentially the derivative, which is also a slope finding formula for any point that I want to, any point in question on this curve. Okay, so if I choose an order pair, and if I plug into the derivative, in return, I'll get the slope. All right, part B, find the points on the graph where there's a horizontal tangent line. So horizontal tangent line is where the slope of the curve is 0. And the slope of the curve is going to be 0, especially if we have a numerator and denominator for our derivative. We're going to set the numerator of our derivative equal to 0, okay, because that's where the slope of 0 will occur. So our numerator is 2 minus 2xy. We can set that equal to 0. So 2 minus 2xy equals 0. 2 is equal to 2xy. So if we solve for, if we group x and y together, we get xy equal to 1. So therefore x equals 1, y equals 1. Well, actually here at xy equals 1, we have two variables. We're going to have to kind of do guess and check to figure out, all right, what x and y value will allow both of these for this equation to be true. Okay. So it'll work when x is equal to 1 and when y is equal to 1. We also want to double check that whatever order pair that we choose, that it will work with the original equation, right? Just because something that works with this equation doesn't mean that's going to exist on this curve. So looks like something easy that we can choose is 1 and 1 for x and y. Let's double check to make sure that works. So if I plug 1 into the equation for x and y, I get 1 plus 1 is equal to 2 times 1, which is 2. So 1 plus 1 equals 2. That checks off. The order pair that will cause horizontal tangent line will be at 1, 1. Right, part C, find the points on the graph where there's a vertical tangent line. So vertical tangent line will occur where the slope of the curve is undefined. So undefined would mean setting the denominator of the derivative equal to 0. So when we do that, we can do x squared plus 2y is equal to 0. So x squared plus 2y is equal to 0. Well, what x and y values can we choose that will cause this equation to be true? Looks like 0, 0 is a good one to choose. So 0 plus 0 is 0. Also, another order pair that could work would be if x was 2 well, actually, if x was negative 2, then we can get this to be 4, and then we can get this to be negative 4, and that will also equal to 0. So this is a little bit of kind of guess and check to determine which order pairs will work. Okay, so 0, 0 works, negative 2 also works. So therefore, we check with the original equation, make sure just because it works for this equation, it also has to work for the original equation. So if we plug 0, 0 and negative 2 into the original equation, we're going to be able to see that it's a point that exists. With the graph, the equation works out. Okay, so 0 equals 0. We get negative 4 equals negative 4. So we have two order pairs that will guarantee vertical tangent line. Okay, number 2, find d2y over dx2. This is notation for asking to find the second derivative. So to find the second derivative, we first need to get to dy dx, the first derivative, and then we can move to the second derivative. So to find the first derivative for x plus 2 over 3 minus x, we can go through quotient rule. So quotient rule is f prime g minus f g prime all over g squared. So f prime times g. So x plus 2's derivative is 1, and we keep the denominator minus the numerator, x plus 2, which is the f, times g prime. So the derivative for 3 minus x, 3 goes to 0, negative x turns into negative 1, all over denominator squared. And if I distribute that through, I'm going to get 3 minus x plus 2, which is 5 over 3 minus 5 over 3 minus x squared. All right, so now we found dy dx, we found the first derivative. Now we can find the second derivative. So to find the second derivative, we could go through quotient rule again, but because the numerator is only a constant, I'm going to move the denominator up. That way I can just use power rule and chain rule. I think will be more efficient. So I'm going to rewrite the dy dx as 5 times 3 minus x to the negative 2. Now I'm going to apply the derivative rule again to get to the second derivative. So to get to the second derivative, let's take care of the exponent. So we bring down, go through power rule, bring down the exponent. So negative 2 times 5, 3 minus x, and we subtract 1 from the exponent. So negative 2 minus 1 is negative 3. And then this is chain rule here because we have more than one term in the parentheses. We have to also multiply by the inside function's derivative. So remember chain rule, outside function's derivative times the inside function's derivative. So the inside function's derivative, 3 minus x will turn into negative 1 because 3 goes 0 and negative x goes to negative 1. All right, so we have our second derivative. We should have to clean this up a little bit. Negative 2 times 5 times negative 1 is positive 10. 3 minus x to negative 3, we can bring that down to the denominator. Okay, and then I just showed another option here where I could have gone through quotient rule and it will give me the same result, 10 over 3 minus x parentheses cubed. All right, last one here, number 3. Find dy dx for 3x plus 1 cubed over 1 minus x squared. All right, if we want to find the derivative, notice that the whole the exponent is over the entire expression. So that tells us that we're going to take care of the outer function first. In this case, we'll take care of the chain rule. Once we apply the chain rule, then we can worry about what's inside the chain, inside the parentheses, and looks at the inside parentheses. The variables are related to one another, or the expression is related to one another by division, so we can go through quotient rule. But first, chain rule. All right, chain rule says outer function's derivative. So that means we're going to bring down the 3, okay, keep the parentheses, subtract 1 from the exponent, so that takes care of the outer function's derivative. Now we're going to multiply it by the inside function's derivative. So the inside function's derivative, we're going to go through quotient rule. So f prime g minus f g prime all over g squared. So f prime, so 3x plus 1 becomes 3, times g, which is 1 minus x squared, minus f, which is 3x plus 1, over g prime. So 1 minus x squared turns into negative 2x because 1 goes to 0 and negative x squared turns to negative 2x. All over denominator squared. All right, so now this whole mess is the derivative. We just have to work to clean this up. So if I distribute the 3 through, distribute the negative 2x through, I'll get 3 minus 3x squared plus 6x squared plus 2x. And then if I try to clean up this expression further, I'll get 3x squared plus 2x plus 3. And now I'm just going to distribute everything through. So everything in the numerator I'll put on the top. Everything in the denominator will go to the bottom. So 3x plus 1 squared, and the resulting of this expression, which is 3x squared plus 2x plus 3, goes in the numerator. And then the denominator will be the 1 minus x squared. Now notice that this 1 minus x squared is being affected by this exponent. So it's 1 minus x squared squared times 1 minus x squared squared. Okay. And then both parentheses are the same expression, so we can combine this even further and make this 1 minus x squared quantity to the fourth. Okay, so now we have everything in factored form. So here's our derivative function.